Right, let's start. So we are currently studying the projector, and one single characteristic or requirement that so that we can call a particular square matrix as a projector is to satisfy this equation, right? P squared is P, which is also called the property of being idempotent, and in this case, P times a given input vector x, that is considered, that is the projection output through this matrix P. And also, let's look at this guy. For any given vector v, and then PV is of course the column space of P, or it is also called the range, right? And in Korean, what's the range? What is this range called in the context of function? So it's 치역이라고 부르죠. So it is called the 치역, which is the set of all the possible outputs when giving any possible input vector, for example v. Okay, and then also in the last time we considered another matrix I minus p. Okay, I minus p, and P is a projector that satisfies this idempotence, and then I minus p is also idempotent, or that is also another projector. Okay, and we can easily verify that. Right, so this guy is I minus 2p minus plus p squared. So this is P, because P is originally an idempotent, right? And then now it is called, it is the same as I minus P. Okay, and so I minus P is a projector, and more importantly, it is called a complementary projector. And the reason is because, so we can think of this range of the initial projector P, and we can think of this another projector which is I minus P, and then what about its range? Okay, so the column space of this I minus P. Okay, so the reason why it is called a complementary projector is because this column space, or the range of this I minus P, is the same as the null space of P, and vice versa. The null space of I minus P is the same as the column space of P. Okay, so what it means is, between the two range or two column space of P and I minus P, there is no overlapping vector except for zero vector. So for a particular, so we choose a V1, and we choose another vector V2. Okay, and then we consider PV1 and I minus P and V2, and then if we consider these two vectors, they are always linearly independent. Okay, so we cannot have any non-zero vector that overlaps or that lies in the intersection between the two column space of I and I minus P, right? So that's how we kind of think of this non-overlapping property between these two column spaces, and also yeah, so in that case we can think of this as this column space of P and column space of I minus P is just 0 vector. Okay, and also what about their union? In their union, it is just the entire space of an Rn. Yeah. So in this case of a union, yeah. So we need a yeah, some special kind of definition, or yeah, how we understand this union in a different manner. So we don't just combine, or yeah, just integrate or incorporate the two sets of vectors into one vectors, but we actually consider their basis. So we have a basis corresponding to column space of P, and also the basis of this column space of an I minus P, and then we union those. Yeah, we just obtain the union of these two sets of basis vectors of these two spaces, and also, and then we consider their span. Okay, so we consider the span of these two aggregated or two combined sets of basis vectors, and then yeah, it will cover the entire space of Rn. Okay, so that is the point. So yeah, it's related to yeah, some kind of basis theorem or the number of bases. So yeah, if we're given the n-dimensional space, and then let's think of the linearly independent, or the number of bases as, yeah, so let me give an example. So if it is 5, and then if it is a three-dimensional yeah, three-dimensional subspace, and then it will have the two-dimensional subspace, okay, and their bases, like 3 bases and the 2 bases coming from each of these 2 spaces, and then combining them and using it as a new basis, and then we can represent any point in Rn, which means that, yeah, by using the 2 sets of bases, we can entirely cover this Rn. So that's the meaning of this complementary kind of subspace. Okay, and this I minus P and P will have this kind of relationship. So so yeah, so let's yeah, let's just prove these two properties. So so here the statement is I minus P projects on the null space of P, which means that for any given vector V, and then we consider I minus P times V, and then that belongs to, yeah, that belongs to the null space of P all the time. Okay, so let's first think of the null space of P, or the element or vector in the null space of P, and then it should satisfy this, right? So that is the initial condition that we start with, and then naturally it is satisfying, yeah, this, because if we just derive it, and then V minus PV, and PV is equal to 0, and thus it will be just V so if we pick up the V, yeah, if we pick up the any particular V which belongs to the null space of P, and then it actually satisfies this, which means that, like, given this matrix, QV is equal to V, right? And what does it mean? This V, original input vector, is actually represented as a linear combination of the columns of Q, right? So through this representation, it is an element, in an element of Q, I mean the range of Q, right? Because it is represented as the linear combination of the columns of Q, which means that it is belonging to the range of that matrix. Okay, so here we chose any vector. We chose a particular vector from null space of P, and then we proved that it is belonging to the range of I minus P. We can also prove the other direction as well. So for any V, let's consider this I minus P times V, which is the projection through I minus P. And then if it is belonging to this null space, which means that we chose a vector from the range of I minus P, and then we assume that it is belonging to this null space of P. Null space of P. Okay, so here, let's see. Okay, so this is not an assumption. So this is not an assumption, but once we rewrite V minus PV, and then we know it is it is it is represented as I minus P times V, which is just a starting point, and then we know that this I minus P let's see. This guy is belonging to the null space. So this is what we proved last time, right? So so in this case, PV minus V is belonging to the null space of P, which is represented as P minus I times V, right? And why is it in the null space, or what's the meaning of this PV minus V? Okay, so it is like so we are given a point V, and in this high dimensional space, if this guy was projected into PV, and then if we consider the origin here, and then we have this original vector, and that is decomposed into this projection part and the remaining part, which is just a remainder after subtracting that projection part from the original vector, right? So that is represented as a V minus PV, and this guy is always belonging to the null space of P, and this is what we proved last time, because if we just multiply this remaining component with the P, and then P squared is equal to P, and thus it will make the resulting vector as 0, right? Okay, so we already know this I minus P times V is it belongs to the null space of P, right? So so that way we proved this range of I minus P is belonging to the null space of P. So we obtained this guy and this guy, and thus these two spaces are exactly the same. And likewise, if we just use I minus P originally instead of P, then we can do the similar proof to obtain this relationship. And also, yeah, in order to consider they are complementary, so we have to understand, yeah, this guy. So their yeah, their intersection is 0 and their union is an entire space. So here a projector P, the null space of I minus P is range of P, which we proved in the previous slide, right? And then given the matrix P, I mean the same matrix P, we consider its range and also the null space, and they always have no intersection between them. So how do we prove that? How do we prove that? So the question is, so we are given this n by n square matrix, right? And then consider it's a null space and also the column space, and they have no overlapping vector. Or yeah, I mean they only have a 0 vector as an overlapping one. So how do we prove that? So that means, so for any v, in order to, in order for it to belong to the null space of P, it should satisfy this equation because that is the definition of the null space, right? And then now, in this case, how can we represent the column space? How can we represent the column space? Another vector that we consider as an element in the column space can be represented as P times V2. So we consider another vector V2, which works as a linear combination of the columns of P. Okay, and then this one can be represented as one element in our column space, right? And then this vector should be also in the null space, which means that this guy times this So let's prove this. So we want to prove that the intersection between the null space and the column space is only the 0 vector. So the vector in a null space should satisfy this, and the vector in the column space should be represented as this, and then this guy should be the same as this guy, because this is our element in the null space and this is our element in the column space, And then in order to satisfy this equation, we need the conclusion that this V1 should be always always zero vector. Always zero vector. So how do we prove that? I thought it's straightforward, but I might be wrong. But yeah, let's just try to prove it together. Can anyone prove it? Yeah, I guess it's not always true. I thought, I think I'm confused that it should always be true for any matrix, any square matrix, which means, for a square matrix, the null space and the column space can overlap. It looks, it seems so. And in order to have a no overlapping between column space and the null space, we need this property of idempotence. So in this case, so we understand this equation as an overlapping element between the column space and the null space, and then let's just multiply P over here, and then we obtain P V1, and in this case P squared V2, right? And then in this in this case we obtain this PV1 Okay, so I don't think I can easily prove it. So let's skip it for now. Okay, so let's just take it granted, and then maybe during the break or maybe later time, I will try to give a proof about it. But if we admit these two are true, and then we can see that the null space of this P and the I minus P, or the range of P and also range of P and the null space of P is has no overlapping vectors, right? And so so here the column space of P and also the column space of I minus P, which, yeah, so we consider two different projector of P and I minus P, and their column space has no overlapping, yeah, the no overlapping element, and also their union is covering the entire space. Yeah, so yeah, it is not a rigorous proof, but yeah, let's just understand it intuitively. And in that case, it is actually separating our Rn into these two subspace, right? And the first subspace is the projection of the original vector, and then the remaining part, okay, this remaining part, which is nothing but just the subtraction or the remainder after we perform the projection, right? So this is our projection through P, and then this is just a simple remainder after this projection. And the interpretation of this vector is that it can also be viewed as a projector, okay? It can also be viewed as a projector, and that projection matrix is I minus P. So that is probably the most important part. So if you are given the matrix, the vector V and some projector P, and then we consider another projector I minus P, okay, and then yeah, do the matrix multiplication on this input vector V, and then those two components, okay, those two components, yeah, has no overlapping components, or yeah, they are always linearly independent. Okay, so they are always linearly independent, which means that the column space of this guy and the column space of P doesn't have any overlaps all the time. And also the fact that the range of this or column space of an I minus P and the column space of P actually sums up to the entire space of an Rn. Yeah, so that fact allows us to represent any given vector in Rn. Okay, any given vector in Rn into, I mean, as a decomposition or the sum of the two projection parts. Okay, so yeah, we are given any vector v, and then pv and I minus p times v. Okay, we can always decompose this vector into these two, sum of these two projection parts. Okay, so that's the meaning of this complementary relationship between the original projector P and the another complementary projector of I minus P. Okay. And also, we know this as a simple relationship of the remaining part after projection. So this guy can be represented equivalently as a v minus pv, which is the remaining part. So that part always belongs to the null space of P, which means that intuitively this projection P cannot see that the remaining part, which means that once we project that remaining part by using the same matrix P, and then you will always end up with zero vector. So this is some kind of intuitive relationship between these two projections. And so in summary, if you have a projection matrix P, and then you always divide your space into two non-overlapping parts, and also their union is summing up to the entire space Rn. Okay, and then it can be written or stated as follows. So P is projector onto S1 along S2. So that means, so this is the direction of our light. Okay, so in this case, so as I mentioned, so all these parallel lines are considered as the direction of light shedding, right? And then that is our S2. What is S2? S2 is a subspace. Okay, so that is subspace, and this subspace is actually the null space of P and also the column space of I minus P. I keep emphasizing the same thing from slightly different perspective. So this light shedding direction, okay, so that always belongs to the null space, okay, and also the projection point and the the subspace that contains all these projection points, which is the column space of P. Okay, so that is our S2. Okay, so we send any arbitrary vector, we send it to the column space of P, which is S1, right? And then how we send it, or the direction of that projection, or that direction of the light shedding, that always belongs to the null space of P. Okay, and so you can think of it in the following manner. So this S1 and S2 cannot just be, they don't need to be a single line. So suppose this is a one-dimensional space and this is a two-dimensional space in our three-dimensional space, because they should cover the entire space. So entire space should be R3, right? And then S1, or the column space of P, we didn't decide, or we didn't determine the particular matrix P, but we just consider this a subspace S1, which is the set of all the projected points. And then suppose that is a single line, okay? And then we consider any arbitrary vector or point over here in the three-dimensional space. And then suppose our projection result or projected point is this point, okay? This point, okay? So this line is, at this particular case, this is the direction of light shedding, right? Right? And this guy belongs to the null space of P, or the column space of I minus P, right? And then what is our S2? Entire S2. S2 is something like this, right? Something like this, okay? So this two-dimensional space is our S2, and then that actually contains those light shedding direction in this particular example. Okay, and then what about the other point over here? So in this case, what will be the projection onto this line? Okay, this comes from different direction, right? Different direction, but that direction, or that vector, which is a remaining part, or V minus PV, right? V minus PV. So that direction should also belong to this two-dimensional plane. Okay. Okay, so we have a single line, and then also we have an origin, and I'm not sure if we can draw properly, but Okay, so so if we consider the point over here, and then this is the light shedding direction, right? And this vector, once we move it as this vector starting from the origin, and then that vector should belong to this this plane, right? And then let's consider some point back there, and then yeah, it is in terms of a depth, it is a little bit it is a little bit further, yeah, back in our space, and then the projection onto this line will be something like this, right? This direction. Okay, so that direction, if we move it as the vector starting from the origin, right? So if we move it in parallel, then that will be like this vector, right? So that way, the projection line, the light shedding direction is not just a one-dimensional. Yeah, it can also be in this kind of two-dimensional stuff, right? So it is all depending on the dimension of our S2, right? And then how about just changing between this S1 and S2? So let's draw another example. Okay, so in this case, so this is our S1. So we have to, yeah, we want to project it, or project any given point into two-dimensional space, right? And that light shedding direction is something like this. So yeah, it is a little bit easy to think of. So if we have an additional point over here, then it will be projected over here. But what about what about these directions, which is indicating the direction of light shedding, and that direction is always parallel, which means that those two are just a one-dimensional vector, right? So that belongs to, yeah, so if we consider the origin over here, and then if we move, yeah, this guy, then it will be like always on this single one-dimensional line. Okay, so that's how we divide the entire Rn into, yeah, one particular column space of one particular projector, and yeah, another light shedding direction which correspond to the projection of I minus p. I mean, yeah, projection through I minus p. Yeah, I hope yeah, it gave some intuition about this projection. Any questions? Okay, and then let's move to this orthogonal projector. So so in the previous case, we considered the general projection where the angle is not necessarily 90 degree, right? But in the case of this orthogonal projection, what's the definition? Okay, so we have some intuition that the projection angle should be 90 degree, but what's the mathematical definition or properties? So that means this non-overlapping subspace of an S1 and S2. Yeah, again, this is the column space of P, and that one is the column space of I minus P. And those two column spaces are, I mean, for general projector, those two column spaces, yeah, we know that they are complementary, which means that they have no overlapping, I mean, only the zero vector as an overlapping element, and then their union is the entire Rn. But when they are orthogonal, then yeah, they are not just overlapping, but also any vector chosen from each of these two subspaces should have the 90 degree angle, right? So that means yeah, you guys know that, yeah, we just separate this three-dimensional space into these two, plane and the line, and in this case we just pick up the vector from one space and another vector from the another space. For example, yeah, so we pick up this vector and then maybe this vector in S1, and yeah, this line is a vector from S2, and then yeah, their angle is not necessarily 90 degrees. Okay? So they still don't overlap at all, but their angle is not 90 degrees. But in order for these two subspaces to be orthogonal, for any given vector that we choose from each of these two subspaces, they should have the 90 degree. And then the only way to satisfy that condition is, so given this S1 and this S2 should be just a line having the 90 degree along any kind of direction, right? Okay, so in that case, you can easily prove this P should be equal to P transpose. Okay? So I leave the proof to you guys, but yeah, the main kind of main sketch of the proof is that we start from P squared is P, which is the property of this projector, and then if the column space of these P and the P I minus P, then it should satisfy this P being equal to P transpose. Okay, so if we satisfy this equation, and then this S2, or the vector belonging to our S2, will be always orthogonal to any vector in the range of P, or in particular this PV is one vector belonging to the range of P, right? So this guy and this guy should always be should always have the 90 degree angle. Okay, so so in this case of the orthogonal projector, original P is represented as P transpose, and also P is P transpose, and so it can be represented as P transpose. So for orthogonal projector P, so that should be always represented as this form. So we can represent this as the main form of this orthogonal projector, but in this case we don't need to have the square matrix in the place of Q in this representation. Okay? So in the three-dimensional space, so let's consider only the two-dimensional, two number of vectors that have the orthonormal columns. Okay, so in this case, it can be representing QQ transpose, right? So once we start with the orthonormal vectors as our columns of a matrix, and then this matrix times this matrix transpose, and their product will work as this orthogonal projectors, because so in this case, let's verify that it is representing, or it satisfies the idempotence. So in this case, the middle part of Q transpose Q is identity, right? And so it is just a QQ transpose, and thus this P is P squared. So we prove that it satisfies the main property of a projector, and also orthonormal. How can we satisfy this orthonormality? So in this case, we don't need to. We just not only satisfy this, but also we need to satisfy P should be equal to P transpose, right? So even though we proved it, but so that is the additional condition that we need to satisfy for this orthogonal projector. And then from this form, QQ transpose, and then if we just transpose it, and then we obtain the same matrix. And so we proved this is also satisfied. So these are the orthogonal projector. And as a special case, if we just have a single vector, single orthonormal vector, which means that we only need a unit vector that has the length of 1. Okay. So in this case, for example, in the three-dimensional space, it is just a Q transpose where the length of Q is equal to 1, right? So that will work as a kind of simple case of this orthogonal matrix. And in this case, let's just understand this intuitively. So so this is our projector P, and then let's consider the projection with the input vector V, right? So in this case, input vector will also be three-dimensional vector, right? And so this input vector is first computed with this inner product with this vector Q, right? And then this guy will work as a linear combination coefficient, Q transpose V times Q, right? So this can be understood as this. So we have this vector Q, and then maybe vector V, right? And then we know once we form this triangle, then what's the length length of this line segment in our triangle? And then it is just a V times cosine theta, right? Whereas theta is over here. Then it is Q transpose V, which is an inner product divided by Q and V, right? So it should be V because the length of this line segment is V, right? And so it is cancelled out, and this guy is what? Is 1 by definition, because we started with the unit vector. And so simply Q transpose V is corresponding to the length of this part. Okay, so when looking at this rank 1 outer product as our projection matrix, And then if we compute the inner product between this Q transpose and V, and then that can be viewed as the length part. Okay, length part. So we compute the length through this inner product, and this, the length of this line segment in our triangle. Okay, and then once we computed this length of this vector, and then we can think of a particular vector as their magnitude or the length, and also their direction, right? So in this case, what is the direction? So direction is Q, right? That has the length of 1, right? And then also, what is the length of this vector corresponding to this line segment? Okay, so that vector is like this direction, and also Q transpose V as the length of that line segment, right? So you can view this projection as these two parts, all like computing first the length of that projection, and then we just multiply or we just impose particular direction, which is our Q, right? Okay, and then we can extend this kind of understanding when we have a multiple column vectors in our Q. So what if we have a 2 column vectors? So the first one and the second one, and the first one and the second one. So this is our Q and the Q transpose, and we are given input vector V. Okay, and then so here we first perform this inner product, and then that is okay. So we perform this inner product with the first direction and this second direction, right? And then we bring this as it is, okay? And that is still Q, and then this part, Q transpose V, is now the inner product part with each of our orthonormal vectors, right? And then now those two values will work as the linear combination with the original vector Q1 and Q2. So this is our Q1 and this is Q2, right? So that they are also the unit vector that has the length of 1, right? And then this part, okay, these two inner product will work as the length of the corresponding vector, right? So we can understand this orthogonal projection in this manner. Okay. Any questions? Okay, so from the perspective of several interesting characteristics that we studied in this chapter about this projection part. So given this QQ transpose, and then this I minus P, which is I minus QQ transpose. Okay. So this guy is also the projection, right? This guy is also a projection, and that is also the orthogonal projection. Okay, orthogonal projection, because if we just compute this guy, let's call it as R, for example, and then R times R is equal to R, and R transpose is also the same as R. So that way, this I minus P is also the orthogonal projection, right? And in the case of a rank 1 case, where we only have a single vector, or our S1, so our S1 and their dimension is 1 in this case, right? because we are just projecting projecting a given vector onto a single vector, right? Single vector Q. So in this case, this guy I minus QQ transpose, I minus QQ transpose. So that that gives us the remaining part after we project a given vector orthogonally onto a particular line. Okay. And so a little bit interesting, hopefully interesting and important part is that this guy is also a projector. Okay, that is projector. But let's consider three-dimensional case, and then this guy or this relationship is quite obvious, and I hope you guys understood this properly, right? So it is just straightforward, just projecting it onto a single line, right? But suppose that vector as one, not one. Square root, 1 over square root 6, 1 over square root 6, and maybe given this vector, okay? So this is one unit vector, right? And then once we form this QQ transpose, and we understand how it works, but once we just form this 3 by 3 matrix, right? 3 by 3 big matrix, and then just to subtract identity, I mean from the identity, which is 1, 1, 1, and 0, 0, 0, 0, 0, right? And then this guy, I mean, it is kind of important. It is important that this matrix will also work as a projector, onto like the remaining subspace where we started from the three-dimensional space, and then our S1 is a single-dimensional or one-dimensional, right? And then S2, which is corresponding to this I minus P, right? So that is still on orthogonal projector onto two-dimensional subspace, right? So given this vector, and then this given this unit vector, and then I minus QQ transpose, and then given a input vector, and then I minus QQ transpose times this vector will actually work as a just intuitively just a projector onto this remaining subspace of this plane. Okay. And we can extend this relationship into much higher dimensional space. So if we are given a single vector in a four-dimensional subspace, for example, maybe over here, maybe this four-dimensional vector having a particular direction, and then we can form QQ transpose and I minus QQ transpose that will project onto the three-dimensional subspace that is orthogonal to this vector. Okay, so you can think of like given this vector, and then we can easily think of the remaining orthogonal subspace like this, which is a two-dimensional, and also in this two-dimensional, any vector from here and this particular line is always orthogonal to each other, right? So we can extend it into the four-dimensional space where we are initially given a single vector, and then now this crossing plane is now three-dimensional space, and that three-dimensional space have any vector, any vector from that three-dimensional subspace is orthogonal to this initially given initial single-dimensional vector. Okay, so let me give some practical kind of usage of this characteristic in maybe deep learning from what I remember. So if you heard about like adversarial attack or adversarial example, so in this adversarial example there are many different like relatively simple methods, and then suppose you are given a particular image which is maybe 28 by 28 and maybe grayscale of 1. Yeah, it is just an amnesty example, right? And then it is represented as 784 dimensional space, right? And then, yeah, let's consider it this point over here in 784 dimensional subspace. And then, yeah, once you give this image into our classifier that classifies 0 through 9, I mean particular digit, right? And then it is actually the digit of maybe 7, right? And then the 7, yeah, we want to make it as a adversarial example. So in that case, suppose this guy is currently having the probability of 80%, right? And then this is the softmax output, right? And then before the softmax layer, we will have a logit value as well, right? And then, yeah, suppose we just incur some gradient at that logit value, so that we want to decrease that logit value to decrease the probability intentionally, so that it can be misclassified as much as possible, right? So minimizing or the decreasing that probability is like, yeah, making this close to like adversarial example that is easy to misclassify, be misclassified, right? So once we just impose the gradient over here, then it will be backpropagated, and then the backpropagation can reach all the way up to every pixel in our input space, right? Which is a 28 by 28, right? So that gradient will have a particular direction, right? So that particular direction is our gradient vector, right? So that is also 784 dimensional space. So what is the meaning of that direction? So once we move that point into that particular direction, then that is our, I mean, the most efficient or optimal direction that we move, so that we decrease this probability to make this as an adversarial example, right? Okay, and then we are given this vector q, and then let's make it as a normalized vector so that the length is 1, and then let's consider this, right? I minus q transpose, and this is our input vector x, and then x, okay? Okay, so so in this case, so given this vector, yeah, given this vector, and then, I mean, what is the meaning of this? So this is the component that are kind of insensitive to that gradient direction, or insensitive means that that component is like an orthogonal component to that gradient vector, right? So if you think of some delta or the additional vector to add to the original vector, yeah, coming from this subspace or yeah, this complementary subspace, and then moving our point along this subspace will not actually change, yeah, will not change this classification score, right? So it is a little bit conceptual or rough explanation, but so we are given the initial input point x over here, and then we determined our gradient as a particular or one-dimensional vector, right? And then we consider its complementary projection of I minus QQ transpose, and then some vector in that subspace or as a result of that matrix multiplication. And then if we move the original point along kind of that direction, and then that can be, yeah, that can be viewed as like insensitive direction that doesn't change the classification score. So does it make sense? Okay, so yeah, let me explain it in Korean in more detail. 네, 그러니까 이게 그레이디언트가 하나가 주어지면 그 그레이디언트 방향으로 이제 우리가 움직이잖아요. 근데 만약에 그 그레이디언트 이런 경우가 있을 수 있어요. 그러니까 그레이디언트, 그러니까 이 클래스 스코어를 직접적으로 바꾸는 방향이 지금 우리가 구한 이 그레이디언트라는 방향이잖아요. 근데 거꾸로 우리가 클래시피케이션 스코어를 전혀 바꾸고 싶지 않아요. 예를 들면, 그러니까 어떤 이미지가 있는데 그 이미지를 뭔가 클래시피케이션 스코어를 직접적으로 낮추는 방향과 그 클래시피케이션 스코어를 전혀 변화시키지 않는 두 개의 방향으로 만약에 분리를 하겠다라고 하면, 그러면 뭐 VA나 뭐 이런 데서 이제 우리가 뭐 랜덤한 그 퍼터베이션을 가해서 이제 다양한 종류의 아웃풋을 뽑고 하듯이, 네, 여기서도 마찬가지로 우리가 저 포인트를 이제 우리가 조금 뭔가 변화를 시킨다고 할 때 클래시피케이션 스코어, 그러니까 우리가 이제 목적하는 요 스코어를 직접적으로 높이 혹은 낮추는 어떤 그 방향으로의 벡터가 있다면 그거에 이제 둔감한, 그러니까 그거랑 전혀 상관없는 디렉션으로 얘를 좀 움직여서 우리가 이 이미지를 좀 더 뭔가 다변화하고 싶은 거예요. 뭔가 좀, 네. 그러니까 뭐 예를 들면 뭐 이런 거죠. 뭐 만약에 6을 이제 0으로 만들려고 한다. 그러면 아마도 이제 그 그레이디언트를 구해보면 여기에 있는 픽셀들은 여기를 지우개처럼 지우려고 할 거고, 여기에 있는 픽셀들은 값을 키우려고 할 거예요. 그래서 이제 어떻게 되냐면 이게 점점 더 이렇게 되고 뭐 이렇게 0으로 만들어지는 거예요. 그냥 이건 가상의 예죠. 뭔가 이런 식으로 그레이디언트가 아마도, 네, 6이라는 거를 이제 서프레스하는 어떤 그런 형태의 그레이디언트는 저런 식으로 뭐 이렇게 움직일 수가 있겠죠. 근데 그거의 인센서티브한 점은 also, yeah, 그러니까 그 컴플리멘터리 서브스페이스로 저거를 어떻게 프로젝션 해갖고 그 방향으로 쟤를 움직인다라고 하면, 그거는 뭐 예를 들면 뭐, 네, 이 6을 뭐 이렇게 더 두껍게 만든다거나, 두껍게 만들려고, 네, 여기 이렇게 뭐 두껍게 더 6을 만들면 사실 이거는 어떻게 보면은 이거 자체가 더 명확하게 6이 됐거나 뭐 더 이렇게 덜 6이 됐거나 뭐 이런 게 지금 전혀 없잖아요. 그러니까 저런 좀 무관한 어떤 방향으로의 어떤 변화의 콤포넌트를 우리가 또 여기서도 뽑을 수가 있다. 네. 이해 가나요? 그래서 뭔가 so yeah, the reason why I mentioned this is because, yeah, I don't remember exactly, but yeah, there were some kind of preliminary paper or early stage paper about this adversary example. I mean, generating adversary example that exactly uses this kind of, yeah, complementary kind of space projection onto the complementary subspace. 네, 그러니까 이제 얘를 이쪽으로 가는 거잖아요. 그러니까 이쪽으로 가면 저게, 그러니까 어떻게 보면 클래시피케이션 스코어를 뭐 낮추는 어떤 그 직접적인 방향이 되는 거죠.
그레디언트는 저희가
여기서 이제
프로페이션에서 얻은 그레디언트.
그렇죠. 네.
그러면 저 그레디언트가 이루는 서브스페이스의 컴플리먼트 서브스페이스를
네.
찾아서 그러니까
네.
저 그레디언트 방향으로 움직이는 게 아니라 데이터를 저 구한 다음에 그 서브스페이스에 있는 방향으로 움직이는.
네. 그러니까 이 방향으로 움직인다는 건 쟤를 하여튼 그 클래시피케이션 스코어를 낮추는 방향으로 움직이겠다는 거잖아요. 저 방향이 지금 저 빨간색 그레디언트가 그렇죠? 왜냐면 저 방향이 이제 우리가 이 백프랍을 통해서 이제 픽셀 각각에 대한 그 그레디언트 값을 구한 거니까.
클래시피케이션을 낮추는 방향으로 로스 펑션이 구성이 되어 있는 건가요?
이거요?
네.
네.
그래서
이 애드버서리 example은 그래요. 네. 기본적으로 뭐 애드버서리 example이니 뭐 저기 스타일 트랜스퍼니 뭐 이런 데서 나오는 기본적인 개념은 이제 우리가 백프랍을 하되 여기 네트워크에 이제 파라미터를 업데이트를 주로 하는데 이제 애드버서리 example 뭐 스타일 트랜스퍼는 이게 이 파라미터는 다 고정이고 이 백프랍을 해갖고 어디까지 오냐면 이 인풋 픽셀까지 와갖고 이 인풋 픽셀에 대한 하나하나의 그레디언트를 구해갖고 이 입력 값 자체, 입력 벡터를 바꾸는 거죠. 그렇게 했을 때 이제 우리가 목적하는 뭐 그건 똑같아요. 클래시피케이션 스코어를 높이든 아니면 낮추든, 네. 아니면 뭐 어떤 특정한 뭐 피처 비주얼라이제이션 할 때도 뭐 어떤 특정한 피처 하나 잡아서 여기서 이제 값을 키우기 위해서 저기서 이제 그레디언트를 여기서부터 1을 플러스 1을 그레디언트를 발생시켜서 여기서부터 이제 백프랍을 하면은 이제 뭐 저거를 높이도록 하는 이 인풋이 어떻게 변화해야만 그게 높아지는가 뭐 이런 걸 구하게 되잖아요. 네, 하여튼 그래서 이게 이제 그런 그레디언트 벡터고 저 방향에 하여튼 수직인 방향으로 움직이게 되면 어떻게 보면 그 클래시피케이션 스코어는 안 변하는 방향으로 우리가 저 데이터를 움직일 수 있다는 거죠. 네. Any other questions? Okay, then let's take a 10-minute break, and then continue at 11:55.
질문인데요. 그 약간 머릿속 이해가 되는데
네.
실제로 어드버서리 그 어택 이미지 만들 때는 그레디언트 어센팅 해가지고 그냥 계속 이렇게 업데이트를 하는 거잖아요. 근데 걔가 컴플리먼트 스페이스로 간다는 걸 저희가 제한시켜줄 수가 있는 건가요? 그런 거랑 상관없는 거죠.
그러니까 저게 내가 무슨 논문을 그걸 얘기를 했냐 아마 한 1년에서 1년 반쯤 전에
네.
연구소에서 스터디한 것 중에 거기 한번 목록에 한번 찾아봐도 될 것 같은데 무슨 스피리컬 이게 들어갔던 것 같은데 애드버서리 example 생성하는 건데
혹시 그 옛날에 성효가 했던 건가요?
두엔이 기억이 안 나고 저 과도관에서 했었던 걸로 기억이 나는데 그게 이제 뭐냐면 그 그레디언트를 구하면 그레디언트 방향으로 이렇게 가잖아요.
네.
근데 그 방향으로 갈 뿐만 아니라 거기서 그거에 컴플리멘터리한 방향으로 좀 또 더 이동을 하는 거예요. 그러니까 이게 그레디언트, 그러니까 좀 랜덤니스를 주는 건데 랜덤니스를 주는 게 일단은 그레디언트는 우리가 여기서 구하는 그 애드버서리 example를 생성할 수 있는 그 그레디언트를 구해서 그 방향을 고지고대로 적용을 해주고 그 다음엔 그게 이 방향이었다 그러면 그 방향 이외에 이제 수많은 그 컴플리멘터리 서브스페이스에서 그 포인트를 옮겼고 그 다음에 거기서 그 컴플리멘터리 서브스페이스에서 그러니까 좀 랜덤한 방향 어딘가로 조금 옮기는 거예요.
그런 논문이 있군요. 네.
네. 그래서 뭐 네, 가고 또 좀 옆으로 가고 또 어떻게 가고 또 옆으로 가고 뭐 이런 식으로 그 하여튼 옆으로 간다는 게 여기서 얘기하는 그런 컴플리멘터리 그거. 그리고 그 옆으로 가는 방향은 어떻게 구하느냐. 그러니까 이 방향에 그러니까 우리가 주어진 그레디언트 방향에 수직인 어떤 랜덤한 벡터를 어떻게 뽑느냐. 그것도 사실 쉬운 문제는 아니잖아요. 그래서 그때 이제 한 게 여기서 요 x를 그냥 쓰는 게 아니라 여기에다가 뭐 그냥 랜덤 벡터를 집어넣어요. 그러면 랜덤 벡터에다 이걸 곱하면 어찌 됐건 그 벡터는 이제 네, 컴플리멘터리 서브스페이스에 있는 거니까.
네.
그래서 걔를 이제 우리가 추가적인 그 변화하는 네, 그걸로 더해주는 거죠.
네.
이게 간단한 거 없었는데 이거 증명이 안 될까?
방향으로 오리지널 데이터를 업데이트를 하는 거잖아요. 그럼 그 다음 스텝은 어떻게 되는 거예요? 그러면 그 다음 스텝에서는 이게 계속 이제 업데이트가 어떤 식으로 그 다음에 이루어지는
네, 그게 이게 지금 조 방향은 이제 특정한 조점에서만 정의되는 그레디언트잖아요. 그래서 저게 좀 로컬리만 밸리드하고, 그러니까 여기서 이제 조금 여기서 막 이렇게 그 부분은 이제 애드버서리 example를 만들어주는 방향으로 옮기고요. 그 다음에 그 얘를 또 동시에 이제 어느 방향으로 옮기냐면 여기 이 컴플리멘터리 서브스페이스에서 뭔가 좀 옆으로 가는 거예요. 저거랑 이제 올소고나랑 옆으로 가면 저기도 요쯤 된다. 그 점에서 그레디언트 또 구하면 또 방향이 나오잖아요. 거기서 또 컴플리멘터리 서브스페이스가 또 나올 거고, 이렇게 이제 로컬로 이렇게 조금 가는 거죠. 어쨌건 이제 안 리니어한 거니까 리니어한 게 아니어서 지금 여기서 이 방향이 딴 데서 다 동일한 그런 방향은 아니니까.
예.
논문을 가장 논문을 보여주는 게 제일 확실한데, 선생님 이거 논문 제목 좀 찾아봐 줄 수 있어요?
어떤 거요?
네? 그 스피리컬 애드버서리 어쩌고 연구실 세미나별 저기 논문 리스트에 있을 것 같긴 한데 한 1년 반은 된 것 같은데. 근데 이거 뭐 중요한 애드버서리 example나 이거 자체가 중요하다라기보다 어쨌건 한 주어진 방향이 있을 때 그 방향으로 움직이는 성분과 그 방향의 수직인 그런 서브스페이스로 어떤 벡터든지 간에 이제 그렇게 두 개를 좀 디컴포즈 혹은 분해를 그렇게 할 수 있다는 거예요. 이게 좀 중요하고요. 그러면 그 다른 방향, 그러니까 한 축으로 올소고나 프로젝션 했고 그거 이외에 가능한 방향으로의 벡터는 어떻게 구하느냐 하면 기본적으로는 어떤 벡터가 입력으로 사용되든 지금 I-QQ 트랜스포즈 요게 어떤 그 n-1 디멘셔널 스페이스로의 프로젝션 매트릭스로서 사용이 됩니다. 요게 좀 여기서는 좀 포인트라고. Okay, so let's continue. Okay, so yeah, I proved this guy. So we want to prove this range and the null spaces, no intersections, and then given the null space definition, this x should satisfy this, and then this x should also be in this range, right? And so it should be represented as a py, which is a linear combination of the columns of p, right? And then y is some unknown, but there should there should exist such a vector y that satisfies this x.
But isn't the y the x, since it's in the range? If x is in the range of p, then x is equals p of x, right?
Okay, so so we start from a vector from the null space, and then that should satisfy this, right? So that's the starting point, at least in this flow. Okay, and then this vector x should also belong to the range, right? And then what is the range? It should be represented as some linear combination of the columns or basis vector. Okay, so from here, because p is represented as a py, and then we just plug in this py in the place of an x in this in this first equation. We plug this in, and then p times y is equal to 0, right? And then p times p is actually p right? And so py is equal to 0, right? And then what was py? What was py? Py is x, right? Which is our starting point, starting vector x chosen from the null space. So this guy is x, and thus, yeah, we obtain the conclusion that x is 0 vector. So, yeah, back to the starting point. We started from some vector x that is not necessarily a 0 vector, but it should be picked up from the null space of P. But we conclude, we obtain the conclusion that such a vector x should be 0, which means that the vector from this, the vector x chosen from the null space of P should always be 0 vector, which means it is impossible to have non-zero vector x. Okay. So this is one kind of way of proof. One kind of way of proof. Questions? So we proved that there is no overlapping, but so the fundamental point that I was confused was that given an arbitrary matrix P, we are just assuming any arbitrary matrix, and then its range and the null space can it looks like it's possible to have an overlap between these two. So because we needed this property of P squared is equal to P, right? So otherwise this vector x from the null space can be non-zero vector, I think. So they can have an overlap. Questions? Okay. Okay, so the arbitrary basis projection to the arbitrary basis is I think we already covered this in the least squares, right? So we want to project some point onto the range of an A, right? And then in conclusion, our conclusion was the projection matrix P, which is an idempotent, so that is represented as this guy. Okay. So again, the point is we want to perform the projection onto the column space of an A, right? Where the columns of an A are not necessarily orthonormal. So in this case, if we just change A into this, then that matrix is our projection matrix that satisfies idempotent relationships, right? And I minus P will also project that point onto the complementary subspace. Oh, and also in this case, is it orthogonal projection or not? So the projection direction, is it orthogonal to the projected subspace, or is it not necessarily orthogonal? So how we derive it is starting from this relationship. So this remaining part is orthogonal to projection vector. So it means that so this guy is belonging to of course S1, and this guy belongs to S2, where the vectors from S1 and S2 are orthogonal to each other. So that was the starting point that we kind of derive this projection matrix. So this assumes orthogonal projection, where S1 and S2 are orthogonal to each other. Okay. Now let's move to this QR decomposition, and also I think I explained this Gram-Schmidt's process, right? Gram-Schmidt's process. So yeah, I'm gonna skip the basic part of this Gram-Schmidt's process to obtain the QR decomposition and move directly to more advanced stuff about this Gram-Schmidt's or QR decomposition. Okay, so it is interestingly, it is related to our projection operator or this complementary projector of I minus P. Okay, so yeah, suppose we are given A1 and A2 and A3 as a set of 3 columns, and then we perform the Gram-Schmidt's process to make it the first orthogonal to the second and the third. Okay, and then, for example, how can we obtain this Q3? Okay, so if you imagine the Gram-Schmidt's process, then from A1, so we subtract the projection part onto the previously built or previously created orthonormal vectors, right? So it can be represented as this A3 minus A3. So this is an inner product operator in Q1 and Q1, right? So this is an inner product which correspond to the length of this line segment along the Q1. I mean, when projecting it onto Q1, and then A3 times Q2 and Q2, right? So this is how we obtain the remaining part, which is orthogonal to Q1 and Q2, and also this is the remainder after we subtract the orthogonal projection onto Q1 and Q2 or previously built orthonormal vectors. And then we just normalize it to obtain Q3. So that is a brief overview of QR decomposition. Okay, and then this guy, let's call it as R3, which represents the remainder after this orthogonal projection. And then we can obtain this R3, okay, R3 through one single matrix multiplication, because this R3 is some matrix multiplication with an input vector A3, and what should be this matrix? So that matrix should be identity minus this guy, Q1 and Q2, Q1 transpose, Q2 transpose. So this is our Q and Q transpose. So we can understand the process of obtaining the remainder part as just the orthogonal projection, okay, onto the complementary subspace to this original projection of Q, which is whose columns are composed of the previously built orthonormal column vectors, right? So this represents the projection onto the orthonormal, I mean the orthogonal subspace, or this is an S2, right? So we can change this QR decomposition part of obtaining or computing this remainder part through this a single one-time matrix multiplication using this complementary projector. Okay, and then using this projector notion of the projector, we actually can think of this alternative form, I mean slightly different form of the Gram-Schmidt process. So let's just have an intuition that this guy, let's see, so let's imagine this the complementary projector. Okay, so in this case, if we build our Q1, and then our P will be I minus this Q transpose, where Q is only containing a single column, single also normal column, right? And then in the next stage or next step of a Gram-Schmidt process, this P, the next matrix P, which is orthogonal, I mean the complementary projector will have the two columns in the place of Q, right? Okay, then our matrix I, and let's suppose we have 3 orthonormal columns. So we are at the fourth step where we handle A4, and then we would have Q1, Q2, and Q3, right? And then I minus this matrix will be our complementary projector, right? But this guy can also be represented as follows, like this. So this is P4, following the notation in this slide, and then it is the same as I minus Q1 and Q1 transpose, okay, and then I minus Q2 transpose, right, and the third one as well. So in this case, it can be viewed as like consecutive projection, okay, onto complementary subspace. So the first projection is like, so once we found one single dimensional Q1, then that complementary projector will project the point onto what is the matrix dimension? Okay, m-1 complementary subspace orthogonally, right? So if we are given a single line in the 3-dimensional space, and then once we project it, then the remaining part is belonging to this 2-dimensional subspace, right? And similarly, if we are given a Q1 in a much higher dimensional subspace of an m-dimensional subspace, for example, 10-dimensional space, and then the complementary subspace will project it onto 9-dimensional subspace, right? 9-dimensional subspace. But that 9-dimensional subspace will not include this Q1 component at all, right? And furthermore, that Q1 will be orthogonal to any vector in the complementary subspace of 9-dimensional complementary subspace, right? Okay, so in order to process or obtain our remainder from this A4, we can just first project it using this complementary subspace that removes this Q1 part or Q1 component. Okay, so that is the result of this multiplication and that vector, that remaining vector, and then we just also multiply this guy. Okay. So this guy, what is the subspace of this matrix? So it is still m-1 subspace, right? So in this complementary subspace, the component Q1 component is actually contained in this subspace, right? But because we just removed that Q1 component by just projecting first it onto complementary subspace, which doesn't contain Q1 at all, right? So that resulting vector will have no Q1 component, and then if we just project it onto like another m-1 dimensional subspace, and then this one will have the projection result which doesn't have Q1 or Q2 either, right? So it doesn't include any of these two. And the third one, yep, can also do the same job, right? So yeah. So in this manner, if you just understood this complementary projector, okay, is the same as just obtaining the remainder, okay? This remainder, which is just naively subtracting from the original vector the projected part, the first projected part and the second projected part. We just naively subtracted that part, right? But we can now understand the way of computing or obtaining R4 as a kind of a matrix multiplication, which is orthogonal, the complementary projection, right? And that single complementary projection represented as this matrix, right? So that can further be represented as a consecutive, like multiple, serial complementary projections. Right? So that is a kind of intuitive understanding. And can we prove this? Okay, can we prove this guy is the same as this guy? Okay, so I leave the proof to you guys, but you can just rewrite these equations as a out of this product form. Then you can just rewrite it, just distributing these multiplications, and then we can just rearranging them, and then we can easily obtain this due to the fact that this Q1 and Q2 or any other two Q's are orthonormal, or their inner product will be 0. For example, if we just consider the product between these two, and then Q2 times Q1 will produce 0, and so that cross term will be gone. So that way we can easily prove this. Okay, so utilizing this serial kind of multiplication using this complementary projector is called modified Gram-Schmitz. Modified Gram-Schmitz. So the original Gram-Schmitz can be represented as this guy. Okay, this guy. So this is P4, and P4 times original vector A, right? And then it is using so this is our remainder vector that I indicate that I wrote as R4, for example. Okay, so this can be now represented as this, right? So what's the difference between these two? What's the difference? So the difference is as follows. In this form, how do we obtain the component corresponding to Q2 or Q1? So in the case of Q1, the component corresponding to Q1, we compute the inner product with the Q1 with the input vector A4. And what about the Q2? Q2 is also combined with, we compute the inner product with the Q2 and also the same input vector A4, right? So in order to compute that corresponding component with respect to Q1, Q2, Q3, we just compute the inner product involving A4 commonly across all the components, right? But in this case, so A4 and its component corresponding to Q1 is computed from this first step, and that is the same as the previous one. But how do we compute the component corresponding to Q2? So when computing the component corresponding to Q2 and subtracting it from the original vector is actually through the inner product with Q2 and the resulting vector over here, not directly with A4, right? So again, the main difference is that when computing the component corresponding to Q2 or Q3, it doesn't directly deal with the original input vector A4, but it's actually like the projected version of input vector through the previous vectors. So we didn't know. We don't know why it is. I mean, what kind of meaning or the meaningful aspect of this difference. We didn't understand it yet, but we at least understand what the difference is, right? Okay, so roughly, so this is kind of pseudocode that represents this classical or original Gram-Schmitz and this modified version. So for each of the previously built QIs, right? QIs and their component, is computed as an inner product with that corresponding component with always this input vector. But in the case of the modified one, this it is computed as an inner product with the VJ, where VJ is the intermediate output like this, and maybe intermediate output like this part. So those parts are called V1, V2, and so on. Okay. Okay, so what changes this in more detail in our algorithm? Okay. In our algorithm, Gram-Schmitz is doing is processing like column by column, given a set of vectors, right? But in this case of a modified Gram-Schmitz, from the perspective of pseudocode, it actually do this some processing like row by row in this part. In this case. So let's look at the pseudocode of this modified Gram-Schmitz. So we start with a set of initial vector A1 through AN. Okay, so we have an m-dimensional vector, and we have n such vectors. Okay, so this is a outer for loop. Okay, so let's start with the first column, like this guy, and then given this remainder, which is given this vector A1, we just first normalize it, right? And then we obtain normalized, simply normalized yeah, also normal vector as qi, right? And then once we obtained q1 through a1, and then this part, yeah, is like iterating through the next one all the way through the end, right? For the second to the last column, which is represented as this for loop, and then okay, so we have a vj over here. So this let me explain it in this manner. So we have a1 and a2 and an, which represents these initial set of vectors, right? And then we obtain q1 as a normalized, also normal vector as the first component, right? And then given the remaining one, we first apply this I minus q1 and q transpose, this matrix multiplication, simultaneously. So for a2, we just multiply with this matrix, okay, and then we have to normalize it, of course, but we don't just handle this a2 in the second step, but we also process in advance all the remaining vectors by just applying this matrix multiplication, because it will be multiplied anyways, right? So it's like so the first one and the second one and the third one and so on. So for the second one, we need to multiply this guy to obtain the remainder part. And then what about this guy? We just apply this guy and I minus q2 transpose, right? So we obtain the q2 over here, q1 over here, right? And then what about a4? These two parts will be the same, and then the third part, will be additional kind of multiplying matrix, right? And so, once we obtained q1, right, and then we just multiply all the same matrix with an input, the remaining kind of, vectors, right? So that way, this guy is called like v2, okay, and this guy is also called v3. And once it is multiplied with this guy, and then this guy is overriding this temporary variable one, v2. Right? This is the overall sketch or overall process of this modified Gramscius. Okay, so once you get this idea, for the remaining columns, then what is this part? Where is our I minus q transpose stuff, right? So it is like, so for example, if we want to compute this, I mean, conceptually, we form this complementary projector of this big matrix, right? And then we multiply A3 or maybe V2. When multiplying with this, we will multiply the resulting vector after this matrix multiplication. So that is, we denote that as a V2, right? that keeps updated. But anyways, so here, so this is I minus Q1 transpose and our vector V2. For example, in this case, we don't actually explicitly form this matrix, because in this case, this one will be really big matrix when we have really large dimensions or large number of rows, right? So the simple computation is like, yeah, so we just distribute it, right? And then we only obtain V2 minus Q1 and Q1 transpose V2, right? So here we are, yeah, obtaining this line segment part, the length of the line segment, and then multiplying with it with the basis vector, and then subtracting it from the original vector, right? Okay, so this part is represented over here. So this is our input vector, right? Then given the currently processed or just freshly obtained Qi, and then we obtain the line segment part, and then subtract it from the V, and we override it into V, right? Okay, so you guys now understand this pseudocode, right? So yeah, just like I mentioned, we just first compute, once we compute Q1, and then we just obtain the outputs of the multiplication with the I minus Q1 transpose with the A1 all the way through AN, and then we store the result, intermediate result as V1 through Vn, and then yeah, in the next step, once we obtain the Q2, and then we just multiply them. So that is the modified Gram-Schmitz, and then why is it good, or what's the difference? I mean, practical difference from the original Gram-Schmitz. So again, the original Gram-Schmitz is just obtaining the this component, this line segment part as an inner product with that orthonormal column vector, orthonormal vector with the original input vector, right? So that's the main difference again. So this is one example of some non-trivial difference between this classical and the modified Gram-Schmitz. Suppose we are given these three vectors. So this corresponds to a little bit tricky case, or they are linearly independent, right? But their angle is really, really small. So yeah, they all have one in the first dimension, and in the remaining dimension they have really small value of an epsilon in each of the remaining dimension. Okay. So in this case, let's just compute the classical way of a Gram-Schmitz. Okay, so this guy is first normalized, and then so epsilon is maybe 10 to the negative maybe 17, and then through our floating point operation, this guy will be just computed as just 1. So if this epsilon squared is this epsilon squared is less than 10 to the negative 16. Okay, in this case, the computer cannot differentiate 1 versus 1 plus epsilon squared if this guy is less than this number. Okay. So that's the kind of main disaster. When this disaster comes into play. So this guy, although this value is not exactly 1, but it is just represented as 1, right? And then yeah, it will be like this guy, right? And then what about V2? V2 is this guy, and then we just compute this line segment part, and then that is 1. This is an exact number, right? Exact number, because this guy with the inner product with this guy is just a 1. And then we obtain this guy, right? Okay, so in this case, if we just normalize it, and then the line segment of that remaining vector is this guy. So yeah, this is the second one. And likewise, the third one, yeah, in the case of third one, we compute the inner product with A3 with each of our previously built component, right? Okay, so in this case, from the original vector V1, V3, or this guy, once we subtract this guy and then we obtain this, and then here Q2 transpose times A3 is equal to 0, right? And so we obtain this. And then the final result is computed in this form. Okay. Now let's apply the modified one. Okay, the modified one. Okay, so maybe you can just follow through eyeballing, yeah, quickly eyeballing the entire process, and then it is certainly giving the different result, where the first and the 3 of these orthonormal basis, orthonormal vector as a result of the QR decomposition is represented as follows, right? And so let's just compare this set with this guy and this guy and this guy. Okay. Okay, so the first one and the second one is the same, right? But the third one is a now different one, right? Okay, and so in this case, let's just check the orthogonality. So in this case, orthogonality between Q2 and Q3 is computed as follows in the case of the classical one, and surprisingly, in the case of classical one, they will not produce a 0 inner product between the second and the third component, right? So it actually didn't give us the completely or perfectly also normal vecters out of these 3 vectors, right? But successfully, this modified one gives successfully the also normal vectors between Q2 and Q3. So what made this kind of difference? So that comes from this part where Q2 transpose times V3 and R23 is Q2 transpose times A3, right? So in this case, A3 is the original vector where really the large value and the small values can exist simultaneously within a single vector, right? So in this case, if we compute this inner product, this inner product with this Q2, then it will produce 0. See, then in this case R23, which is the inner product with this V3 with Q2. See, it's Q2. So this guy, and where is Q2? V3. So this guy. So the remaining part of this V3, which is just subtracting the previously built component, and then computing the inner product with this guy and this guy, and then it can still produce some small values like this, right? Some small values like this, but in this case, their inner product is completely viewed as 0. Let's see. And then why is the so where is this error coming from? So yeah, let me just give a brief reason, reason about this. So when just using this A2 and A3 as it is, when computing their line segment part with the previously built vector component or the orthonormal basis vectors, okay, previously built orthonormal basis vectors, and their inner product with these input vectors, and then these input vectors will have a really significantly different, I mean those values that has a significantly different scales. So in this case, their inner product can be computed like inaccurately. So in the case of this modified one, once we compute the remainder first and then applying the process of computing the line segment with the next orthonormal component, and then it leads to like more accurate computations. So in general, this modified Gram-Schmidt process is giving more stable solution. Especially when the vector vector angles are really small. Okay. I thought I mean there is a clear kind of step, but I don't easily see it right now. So does anyone know where exactly this approximation or like inaccuracy comes from? So up to this point, the results are exactly the same. So 1.
R2, 3, right? R2, 3 becomes different.
Right. Yeah, I tried to figure out why it became different, right? So, okay, so yeah, this A3 has a 1, 0, 0, and epsilon, and our Q2 has the component, non-zero component in the second and the third dimension, right? So in this case, if we just compute, yep, the inner product with that one, then yeah, we obtain 0, and then from the inner product with this guy and the original vector, yeah, the inner product is exactly 0. So this particular step itself doesn't have anything wrong, right? Anything wrong. So the reason is because, yeah, the reason is because this R11, as I mentioned, so this one is not reflecting the exact length of our vector, right? So our length of vector should be this guy, but it is approximately represented as 1, right? Then, so that's how we obtain this Q1, right? And then the projection, I mean the component corresponding to Q1, yeah, I mean given A3, then if we compute the component corresponding to Q1, and then that component will be inaccurate, right? Because our Q1 was computed like inaccurate, like not exactly satisfying the length, length being 1, right? So that actually creates the problem. So yeah, I cannot give a kind of clear explanation at this point, but yeah, at least you guys know the shallow level difference, or the computation. You guys can follow these steps, step by step, and then you can see the clearly different result from these two approaches. And so in this case, in general, this modified one provides the better numerical stability, where this epsilon plays its kind of critical role. Okay, so and also in general, this epsilon part is I mean the approximation happens at this particular step, right? 1 plus epsilon squared is actually approximated into 1. But in this case, their difference between left and the right values are really minimal, right? So up to this point, although approximation happened, it doesn't actually create a big impact. But the big impact happens in this place of like, so when computing this remainder from the second vector, and then now this remaining vector is composed of all the small values, right? Negative epsilon and positive epsilon, and we compute their lengths as this form, and this length or this small value is actually working as divisor in our normalization of this vector, right? So initially this remaining vector was really small vector, I mean in terms of their lengths, right? So because they are small, we can kind of tolerate, or we can kind of we can kind of admit, or we can kind of bear small differences, okay? But through their normalization in terms of their unit length normalization, and then this small difference is actually magnified, right? So that is exactly happening through the division by close to 0, right? Close to the number close to 0, right? So this kind of numerical stability, or the finite number representation used in our computer is all like happening through this exact step of dividing the value close to 0, right? Because even though that was a really small value, when dividing some value by that, then depending on that small value, or like a little bit bigger or smaller than the true value, and then it will create a really big difference, because it will just multiply the value with a different ratio. Okay, so those kind of numerical linear algebra, or any other kind of numerical, those advanced algorithm that handles this numerical issues is all like the main purpose is to better handle this division by the number close to 0. Okay, so you guys know how to compute the number of flops, right? So the number of flops is the total number of summation, addition, or subtraction, or summation, subtraction, division, and multiplication. So each computational step is considered as is counted as just one single operation, and then if we just compute the total number of summations and the multiplication and divisions and so on, so that is representing the number of the flop count when describing the computational complexity of our algorithm. So by following each of our pseudocode, you can easily compute this number of arithmetic operations. And so I will just skip this part and move to the next chapter. So the next chapter is about different way of computing the Gram-Schmitz. So the first one that we will study is called the Householder reflector, and the second one is the Gibbons rotation. So in the case of a Gram-Schmitz process, So you can view it as a kind of sequence of the projection onto also normal basis that we obtain one by one, right? And then the remaining vector is just through this complementary projection, or just subtracting these projected part from the original vector, right? And so the main operation is this kind of also orthogonal projection done in this Gram-Schmidt process. But in order to compute this QR decomposition, we can also utilize some other operations called reflection and also rotation. So rotation is just a simple rotation that you know, like cosine and sine and sine and cosine, and we put negative sign over here, right? So in terms of a high-level overview, let me just describe this given rotation first briefly. So how can we so we want to perform the high-level rotation, okay? High dimensional rotation. So in the case of two-dimensional case, we know this is the rotation matrix, but what if we want to perform the rotation in more than two-dimensional space, right? So in that case, we can just rotate only the two-dimensional along the two-dimensional at a time. So we basically embed this two-dimensional rotation matrix into much higher matrix. So given maybe three-dimensional vector, for example, and then let's just rotate maybe 30 degrees by only using the first and the third dimension. And in the case of second dimension, we can just leave it as it is. Okay, we just want it unchanged, and then how can we build such a matrix that only applies to rotation on the first and the third dimension? So in this case, we have this two-dimensional rotation matrix into this higher dimensional matrix, where we just put this value, cosine theta and sine theta and sine theta, sine theta and cosine theta in the corresponding dimensions. So again, we want to apply the rotation in the first and the third dimension, and we just put those four elements in the first 1, 1 and 1, 3 and 3, 1 and 3, 3. And then what about the remaining part? So let's just think of the resulting vector. Then this guy is the rotation of this guy and this guy, right? So if you just think of the inner product, then what should be the value over here? It is 0, right? Okay. Then let's think of the third dimension, which is also the output of this rotation by involving the first and the third one. Then it will also be 0, right? And then what about this row? Okay, this row, we just put 0, 1, 0, right? So that we just leave this one unchanged, right? So this is the two-dimensional rotation embedded in much higher dimensional space. Okay, and then in general, we can form this kind of matrix in the following manner. So we have m by m matrix, and then we just start with an identity matrix. Okay? and then all the off-diagonal parts will be all 0. Okay, and then if we want to apply maybe i's and j's dimensions, I mean rotations on these 2 dimensions, and then we pick up the 4 elements I comma I and j comma j and I comma j and j comma I, and then we replace those 4 elements by using these cosine theta and sine theta and so on. Okay, so if you just imagine this kind of process of multiplying the input vector on the right, then you can just understand it will produce the i's and j's dimension as a rotated output and the remaining dimensions as unchanged. Okay, so in the case of this given rotations, it utilizes this kind of 2-dimensional rotation. Okay, so we will see more details. And in the case of householder reflectors, so just like the operation of the projection and also the rotation, which both of which are represented as matrix multiplication, this reflection can also be represented as a matrix multiplication, which means that this reflection is also a linear transformation. Okay, so let's see. Let's think of this kind of scenario where we are given some hyperplane H. So that hyperplane has the normal vector as V. Okay. So in this case, how do you obtain this projection onto this hyperplane? Okay, so we want to apply the orthonormal projection of this orthogonal projection of the input vector x onto the hyperplane that we are given, and this hyperplane in general is in m-dimensional space, and then the hyperplane the dimension of the hyperplane is m-1, and this m-1 dimensional kind of hyperplane has the property of a single particular vector, okay, one-dimensional vector that is orthogonal to any vector in this hyperplane. Okay, so that is that's how we define this hyperplane. Okay, so I think I described this in our class, but yeah. From our high school, we know that this is a equation for the plane in the 3-dimensional space, right? And then, ignoring D, because D is just y, the intercept that actually moves our hyperplane in parallel. Okay, and then let's just simplify it as having 0 for this value of D, and then it is represented as A, B, C, and X, Y, Z. So in this case, our hyperplane is all the points orthogonal to the vector pointing to A, B, and C, right? And so in And if this value is d, for example, and in this case you can think of the same value, okay, same values as like shifting like vertically along the last dimension. Okay, and, yeah. Yeah, although it should be negative d, but yeah, this single linear combination representation is actually corresponding to a particular hyperplane in the high dimensional space. So in this case of three-dimensional space, all the vectors that are orthogonal to this given particular vector of A, B, and C, and then it will form the two-dimensional subspace. And then in the case of like four-dimensional subspace, AX plus BY plus CZ plus DW plus E equals to 0, and then if we ignore this part, and then it is still represented as A, B, C, and D, and then X, Y, Z, W is equal to 0. So that way, this hyperplane in the four-dimensional space is all the points, the set of all the possible points that have the inner product with this A, B, C, and D as 0. Okay, so this vector is called a normal vector of a hyperplane, right? And yeah, in the three-dimensional space, all the points that is orthogonal to a single vector is forming a two-dimensional subspace. In the four-dimensional subspace, our hyperplane will form three-dimensional space, right? And in the case of m-dimensional space, if we have one particular vector, that should be orthogonal to the vector in our hyperplane, and then it should have m-1 dimensional subspace. Okay, and so given this hyperplane that is orthogonal to or that has the normal vector of V, and then we can obtain its projection onto this hyperplane, and also we can further think of their reflection. Okay, reflection. So the reflection is defined as follows. So in the two-dimensional space, this is our one-dimensional hyperplane, right? And then that normal vector, is in parallel to this projection line, and then suppose X was projected onto this point, right? And then we move this direction once again along the same direction, and then we obtain the resulting vector that is on the other side of this hyperplane that has the same length between this point and the hyperplane and the other point in the hyperplane. Okay, so this is the reflector. Okay, so how do you obtain this reflector operator as a linear combination? Let's first think of the projector. Okay, so once we obtained this point as x hat, and then how can we represent this reflected point? This reflected point is as follows. So x and x minus x hat. So this guy, negative this much will result in this x hat, right? And then we move the same direction with the same amount once again, right? And so we just multiply it by 2. So this one will give us the reflection point, right, with respect to this hyperplane. Oops, yeah. So it should be x hat minus x, right? Because the starting point is x and the ending point is x hat. So this vector is represented as x hat minus x. Okay, so how can we obtain this x hat? Or the projection onto this hyperplane. This hyperplane has the normal vector of this given vector v, right? And then this v vector from the perspective of a projector, and then it will work as our complementary projector, right? Because that is corresponding to the direction of shedding light, right? Okay, so in that case, I minus V and V transpose, right? And this is not it because we do not have the unit length assumption of this V, right? So in order to have the unit length assumption, we need this as our normalizer. Okay, so this guy is our projector onto this hyperplane that has the normal vector as V. And this guy times x is our x hat, right? Okay, so let's just plug this x hat into this part. And then it is 3x minus 2x hat, right? And then this guy is plugged into this part. Okay, and then 3i minus 3i times x minus I times 2i times x plus VV transpose and 2 times x. Okay, so we have a single I over here and then plus this much, right? So why do we have the plus sign over here? It should be minus. So overall, yeah, we want to obtain this relationship, I minus 2 times VV transpose over the norm squared of V So where am I wrong? Over here? Why do we have a plus sign over here? Minus. Maybe I'll find the mistake maybe later time. And then so the time's up. So let's stop here for today. Okay, and then we will continue next Wednesday. Okay, thank you.
이게 반대가 아닐까요? x 마이너스 x 아닌가요?
그럼 그게 이 방향을 나타내는 거잖아요.
네. 그래서 그렇게
그러네요.
하면 풀리는 것 같아요.
아, 그러네요. 아, 이거 왜 이렇게 했지? 네, 여기서 이거 이렇게 하죠. 그러니까 무슨 의미냐면
네네 플러스라고 계속 똑같은 거.
네, 이게 이 방향이면 이걸 플러스를 해야죠.
네.
네. 그러면 나와요?
네, 똑같이 나오죠.
아, 네. 그러네요. 네. 고마워요.